Previously in class, we've seen that a system can be represented by a differential equation. This differential equation can have only three kinds of things in it: the input signal and its derivative, the output signal and its derivatives, and constants. We've also seen that these differential equations can get pretty complicated pretty quickly. Furthermore, we've been determining system behavior, that is, seeing what the output signal looks like, by creating a simulation in Excel with a time step. This isn't the best way to predict the output signal because anytime we use a difference equation, that is the time step method, to represent a differential equation, the output won't be completely accurate. In this section of class, we will be learning a mathematical solution for these problems, a way to simplify our equations and to find the exact solution to a differential equation so that we can see what the output signal will exactly look like, not just what it will approximately look like. Our process of simulating the output will become much easier, and this mathematical approach is called the Laplace Transform. The Laplace Transform has a lot of nitty-gritty mathematical details underlying it, which we will get into in a future video. But for today, I want to give you a feel for how the Laplace Transform is used and how it is useful. To begin with, let's look at some simple Laplace transforms. The real power of the Laplace transform is that it converts a derivative of a time function into multiplication by a new variable s, so that differential equations in time become algebraic equations in s. I think it will become more clear what this means if I give you some examples. So to start out with, let's look at the standard form of the second order system, which you're pretty familiar with by this point. This is a good system equation because it only has those three things that were allowed: the input signal, written here as x of t, the output signal, written here as y of t, derivatives of the input and the output, and constants. However, this kind of an equation is pretty messy to work with. The only way to predict the output for any given input is to create a simulation the way we've been doing in Excel. Also, we know that we could put this system together with other systems in a block diagram the way we did with the helicopter problem in problem set 2. But that approach gets pretty messy. We have to be substituting in for different variables, we have to be taking derivatives of different equations. It can get complicated and hard to keep track of all of our variables. Instead, let's start by taking the Laplace transform of this equation. In the Laplace transform, the derivative of a variable becomes converted into a variable called s. So let's start over here on the left. The second derivative of the output signal y of t, after we take the Laplace transform, becomes s squared, because we've taken the derivative twice, times the variable y of s. I've changed the lowercase y into a capital Y, and I've replaced the time variable with the s variable. This represents the Laplace transform of our output signal. The two s's represent the fact that we're taking the second derivative of that variable. Now let's move on. The Laplace transform of a constant times a variable is just the constant, so we don't have to change these constants at all. X of t simply becomes x of s. I don't multiply or divide this term by s because x of t does not have the derivative. It's not the derivative of x of t, it's just x of t. Next, we have the variable y dot. In this case, I'm going to keep the constant, and I'm also going to multiply by s, but only one s, not s squared, because I'm taking only the first derivative of y. Lastly, I have omega n squared and then y of t, which becomes y of s. Again, no variable s becomes multiplied by this term because I'm not taking the derivative of y at all. You'll notice that in my new equation, we don't have any derivatives at all. In other words, this isn't a differential equation at all. It's just an algebraic equation. So why would this be useful to us? Well, there are two reasons in particular. Reason number one is that it's easy to find the output for any given input. In the next video, I'm going to be going into this in detail to show you how you can use the Laplace transform of an equation to find the output for any given input. The second reason why this is useful is because it's easy to string together systems in a block diagram. In the third video in this series, I'm going to show you how we can use the Laplace transform of a differential equation to make it easy to combine systems together in a single block diagram.